let's look at volume of a solid formed by the rotation of curves. Okay, so let's see what we mean by that. I want to keep it parameterized, and when we rotate a curve, we require the third dimension as well. So let's go for the 3D calculator. Okay, and I want to parameterize it, so let's use sliders. Slider from -5 to 5 in steps of 1. B is equal to slider from -5 to 5 in steps of 1. Let's define these two boundaries as planes so that we can actually visually see it. So x equal to A is one plane and x equal to B is another plane. Now both these planes lie on the same, right? They are the same plane. So volume would by definition be 0. So let's increase it to 2 and let's increase this by 1. So now you can actually see there are two planes. We are only interested in what happens within this gap. Okay, now let's define a curve. So we have boundaries defined on two sides. The third boundary will be defined by a function. So if A is less than or equal to x, which is in turn less than or equal to b, x square. Yes. So this is our third boundary. And we want the fourth boundary. Now let's say the fourth boundary, again we want to parameterize it. So let's say boundary equal to slider from say -5 to 5 in steps of 1. Now let's actually define the boundary. So h is equal to this would be a segment. Let's say for a segment we require 2 points. So a comma boundary comma 0, and the second point would be b comma boundary comma 0. So as of now the boundary, the fourth boundary lies on the x-axis itself. No issues. Later on we'll see if we change it what happens. Now what are the next step? Ultimately we have to rotate it around an axis of rotation. So let's again have a variable axis of rotation. So axis is equal to slider, let's say -3 to 3 in steps of 1. And let's actually define the axis of rotation is equal to this would be again a segment with 2 points, and what those points would be is a comma axis comma 0 and b comma axis comma 0. Yes. So now again if you notice the both the axis and the boundary, they lie on the x-axis itself. Now if I change this to 1, you see this. Now let's change the color so that we can visually understand this better. So let's say color is, let's say, brown. The curve is dark blue. This is brown, and the black is our axis of uh, no axis of rotation is brown. So let it be 0, and let this be, and let's change this color to let's say green, right? So this curve defines one boundary, this green segment defines another boundary, and these two planes define the third and fourth boundaries, and this brown one defines the axis of rotation. Now what happens if we rotate this? Now to rotate it we require an angle. So let's define an angle slider from 0 to 2 pi, that is complete circle, in steps of 0.001. And now we rotate what? F by this angle around an axis of rotation, right? Okay. We also have to rotate the green boundary. So rotate, that is green is H, by this angle around the axis of rotation, right? Now let's see what happens. Okay, now if I rotate it, what happens is this, right? But you can't actually make out the shape that is being formed. So for that, let's ask it to preserve the trace. So it will retain the each curve as it rotates. Okay, and let it also show trace. And now let's start this again. So if I rotate this, you notice here you have a cup and you have a small cylindrical emptiness in between. So we have to figure out the volume, yes, by taking the integral of this slices of circles of blue and subtracting from it the volume found by integrating the slices of this green. Okay, so that is one. Now here the axis of rotation was the x-axis. Now what we'll do is we'll change this. Let's change the axis to 1 and let's see what happens. Right? So instead of on the x-axis, it is rotating around y is equal to 1. Remember, we are rotating both here. In the previous case, this green curve was forming a cylinder. But here, it is not forming a cylinder. It actually doesn't form any, because the axis of rotation and the second boundary was the is at the same place. So when it rotates, it doesn't form a volume. Okay, so that is another way of looking at it. We can actually play around with lot of such. So let's increase this. So what happens? The figure becomes larger, so naturally your volume will also increase. It looks like a rectangular area, but it is not. It is just the diagram boundary which is cutting off these lines. Okay, now another very interesting way of doing this is if we keep the axis of rotation and the boundary, straight line boundary, separate. So how do we do that? Let's say axis of rotation is yes. So let's take it like this. So our axis of rotation is the x-axis, but now you notice green bars we have two. Actually, if I ask it not to display the rotational, and so this is what we get. So this is our axis of rotation. This is the boundary, one boundary. This is the second boundary. This is the third boundary. These are vertical boundaries. This is the function boundary. This is another function boundary. Now, if we rotate it, what happens? So again, we end up with a hole in the middle. Okay, this I think we had already seen this. Now what we'll do is let's change this. Let's take it to 0. If we take it to 0, what will happen? Let's again rotate. So here looks same what we had, maybe a little bit different, but it's a blue shape minus the cylindrical this one. Okay, but on this side we have to also figure out there is an enclosed space between the blue and the green. So that also that volume also we have to evaluate. So as you notice, with very specific set of values, the calculations would be simple. But slight change of parameters, you would end up evaluating the intersections of curves, figuring out and then splitting that into two parts. That is the x values. You are going to have in different intervals. For each interval, you are going to evaluate the area, then integrate that area, and then finally add up all the volumes. Okay, so that is volume of a solid formed by the, and it actually is a solid because solid in the sense as enclosing space, right? So you have one boundary, second boundary, third boundary, and you have a fourth boundary. So the enclosed space between these boundaries is what we are talking of. Okay, that's it. Bye.